On the 19th of September 1985, an earthquake of magnitude 8 hit Mexico City. In memory of this devastating event, an earthquake drill took place on the 19th of September in 2017. Just a few hours later, a magnitude 7.1 earthquake located near Ayutla, Puebla, Mexico, caused near enough equal devastation, resulting in at least 44 casualties. Research suggested that this was caused by a rupture between the slabs in the Cocos Plate lithosphere. However, the deaths were not caused by the earthquake, but rather by the precautions that engineers failed to take in case of an earthquake. Seismic resistance is an especially important feature of buildings in places such as Mexico, which fall within one of the world's most seismically active regions, commonly referred to as the Ring of Fire. Buildings are often designed to take vertical loads, such as their own load and the load of objects inside it, but not large horizontal loads caused by earthquakes. In this presentation, we will explore two sectors of engineering that is responsible for ensuring the safety of the people in case of an earthquake like this: structural engineering and geomatical engineering. Good structural engineering ensures the stability and functionality of structures such as buildings and bridges. This is Santa Ana Avenue that failed during the 2017 earthquake in Puebla, Mexico. In our workshop, we replicated the basic structural features of this building and added aspects that increased its ability to resist the lateral load of earthquakes. This included bracing and making sure the second story was not heavier than the first. We also made the columns stronger than the beams, as the beams are less important in keeping the structure safe. Our construction was then put to the test by applying large lateral loads onto it. The foundation and ground force stayed strong, and thus the egg that was placed on the top story was left unharmed. This meant our structure was successful in resisting seismic activity. Geomatical engineering is concerned with the behavior of earth materials. Its significance during an earthquake lies when the slope stability is not ensured and the slope failure occurs. If this happens in a residential area where buildings are built on top of the slope, it may damage the structures and cause fatalities. In a second workshop, we analyzed the slope stability of materials from Luis Donaldo Colosio Avenue by calculating the angle of repose of sandy material from Mexico City at different accelerations. We attached a mobile device to the container in which we constructed the sand slope. We used an app to measure the acceleration when the container was pushed. Using a graph of angle of repose against acceleration, we could estimate the factor of safety. For a safe slope, the minimum value of the factor of safety should be 1.2. There are an array of geotechnical failures that could potentially occur, for example, subsidence, liquefaction, and tilting. However, there are also many ways engineers can ensure the safety and stability of structures so that natural disasters such as earthquakes do not turn into devastating situations like the 2017 Puebla, Mexico earthquake.